different about the green column versus that purple one? What do you notice is different?
There's like something going on with the X, like extra.
Awesome. Okay, there's something extra going on with the X. So do you see here in the first one, y equals the square root of x squared plus 1. I have a square root is the outside function and inside, so it's really a composition of functions here. In the second one, I have sine is my outside function and 6x is the inside, but there's some, and I like how you worded that. There is something going on with the x. It's not just an x. Look at the third one. Y equals the quantity 3x plus 2 to the 5th. So I have an inside that I'm putting into something to the 5th power. And then here I have a sum, and so what's really cool is we can do our product rule, our quotient rule, and embed the chain rule. So it's very exciting. So here the x is no big deal, but I put an x squared inside the tangent function. All right, so here we go. I'm really going to break this down. Okay, I'm breaking it down to the simplest parts for you. So in this table, it says complete the columns in the chart below. So in letter A, I have y equals 1 over x plus 1. So we want to know how would you rewrite this using parentheses. So I could rewrite this as y equals x plus 1 to the negative 1. So now, and I want you to think about your charms blow pop. We want to identify what's the gum, what's on the inside. Well, the inside here is x plus 1. Okay, what's the candy shell around it? What are we doing to that? We're raising that stuff to the negative 1. So we're going to call it y equals u to the negative 1. All right, letter B. If I want to rewrite this using parentheses, and the parentheses are identifying the inside or the gum in our charms blow pops. So u is going to be the inside or the bubble gum. What are we doing to this bubble gum? We're taking the sign of that input. So y would be the sign of u. Letter C. I'm going to put the 3x squared minus x plus 1 to the 1/2 power. So what is u here? What is the inside? Good job. 3x squared minus x plus 1. Well, what are we doing to that inside? Good job. We're raising it to the 1/2 power. All right, letter D. Don't let this bother you. When I see tangent squared x, that is just the convention, the way that we say that's tangent x, the quantity squared. So what is my inside? What's u here? Tangent x. What are we doing to tangent x? Squaring it. Okay, so now watch this. And I want you to write this over here to the right. dy dx is equal to dy du times du dx. I want you to write this. This is what was up in that box up there, in the blue box. And what I want you to sort of identify here is that if I do dy du times du dx, the du's cancel. And that will give me dy dx. dy dx is another way to say find the derivative of y with respect to the variable x. So dy du represents the derivative of y with respect to u. du dx means find the derivative of u with respect to the variable x. That's what that notation means. All right, so let's go ahead then, and what I want you to do in example 2 is stay with me here. The first thing I'm going to do is I'm going to identify the inside. We're going to call the inside u, And then the outside is u cubed. Now I'm going to only show you this on one problem, and then we're going to work with the shortcut from then on. But I want you to understand like the why this works, okay? So watch what I'm going to do. I'm going to find the derivative of u with respect to x. So we call that du dx. So that's 2x. I'm going to do dy du because that's going to give me the derivative of y with respect to u. So that's 3u squared. All right, so now we're going to come back over here to the right. And if I want to find dy dx, that is dy du, so that was 3u squared, times du dx. Well, u is x squared plus 1. So I can multiply the 3 and the 2x because they're outside of the parenthesis. And I would get a final answer of 6x times the quantity x squared plus 1 squared. Now, sometimes you will be required to use this technique. Like they'll do some things to you where you're forced to use this. So it is going to be important that you do understand this. All right, however, there is a shortcut. Okay, there is a shortcut method, and I personally use the shortcut. Some of you, I think, will pick it up easily, and you're going to go, yes, I'm using the shortcut. Some of you, the shortcut will be confusing, and you can always go back to this technique I just showed you. So, I will not make you use one versus the other. It's whatever's going to work in your brain for you. So watch the shortcut. Here's the shortcut in that blue box below. Here's what it says. You bring down the power, decrease the power by 1, and find the derivative of the inside. Let me go through that again. It says, bring down the power. I leave the inside alone. Remember, we can't get to the gum. Can't get to the gum until we take care of the outside. So I bring down the power, decrease it by 1, and then now I'm ready for the gum, and I can take the derivative of that inside. And notice that is the same and way faster, okay? So let's look at example 3 then, and I would prefer us to do the shortcut. So dy dx, I'm going to bring down the power, decrease the power by 1, and then take the derivative of the inside. Now, a question you might be asking is, why didn't we do the chain rule before? That's an excellent question. All of the derivatives we did before, the derivatives of the insides were 1. So we didn't bother. It was like x or x plus 5. Those all had derivative 1. So that's why we didn't mention the chain rule yet until now. Now we're ready to go up a level. So, and this is an acceptable answer. In letter B, I personally would rewrite this before I do my derivative. So I'm going to write y equals the quantity x squared minus 1 to the 2/3 power. All right, I'm going to pause, and I want you to try this. All right, talk at your table on B. See if you got the same answers as the people at your table. All right, so here we go. I brought down the power, decreased the power by 1, and then took the derivative of the inside. This is an acceptable answer. However, I doubt that's what it would look like in a multiple choice. If I had to guess, this is what an answer might look like. 4x over 3 cube root x squared minus 1. All right, letter C. Before I start this one, I would rewrite it so that it's in power rule form. So power rule, product rule, quotient rule, all can contain the chain rule within it. So let me give you a head start and go ahead and try this one if you haven't already. All right, I'm going to bring down the power, decrease the power by 1, and then take the derivative of the inside. So if I tidy this up just a little bit, that's 28 over 2x minus 3 cubed. Can you guys show me thumbs up? Did you get it? Whoop, whoop. Okay, cool. All right, so now we're going to refresh. And what's so cool about the chain rule is we're reviewing power rule, product rule, quotient rule, trig. We're going to do natural log, e to the x. We're going to do all of them again, but incorporate the chain rule. So the big idea here for the chain rule for derivatives is all you do is take the derivative of the trig function, leave the inside alone, and then take the derivative of that inside. So no big deal. So look at example 4. So if it helps, rewrite it like this, y equals sine 2x. Now, do you remember that dy dx is the same thing as y prime? You can do them interchangeably. In that first one that we did, when you're doing the u and the y, then you really do have to say du, dx, dy, du, because you're saying what letter are you taking the derivative with respect to, but y prime means dy dx. So this will be cosine of 2x times 2. All right, I'm going to pause a moment, and I want you to try B and C. All right, what is the derivative of cosine? Nice job. Negative sine. I leave the inside alone, and then the chain rule says take the derivative of the inside. So that's negative 3 sine 3x minus 1. Make sure you do have parentheses there. All right, y prime. What is the derivative of secant? Secant x, tangent x. So I'm going to do secant 4x, tangent 4x. Now, I need to make sure we don't get confused here. So I'm looking at my original function. Y equals secant 4x. I take the derivative of secant, leave this stuff alone. Now I'm looking at the original, and I'm doing the derivative of that inside. I'm not doing the derivative of both of these. Okay, that's not what happens. So then I multiply by a 4. Okay, so now we're going to get through example 5 and halfway through example 6. It's not uncommon for certain compositions of functions to require 2 uses of the chain rule. So this is why some math AP Calc teachers use peanut M&Ms or the charm flow top. I opted for the charm flow top because I like the layering here of you have the wrapper, then you have the candy shell, and then you have the gum. So that is going to apply to the repeated use of the chain rule. Now, my experience has been we only see like a double use of it, even though I'm going to give you some that might have a triple use. Typically, it might just be a double use. So let me show you how to do this in example 5. So the first thing I'm going to do is I'm going to rewrite the function, okay? I'm going to try to move nice and slowly here to get you to stay with me. I have, this is really y equals the sine of 3x to the 4th. So here's where I want to connect this to the term flow pops again. So something to the 4th power is the wrapper. Okay, that's the wrapper. I've got to take off the 4th power first. Then the candy shell is the sine function, and the gum is the 3x. Does that make sense? I've really got 3 layers happening here. So watch how I'm going to find my derivative. And again, it does not matter if you do y prime or dy dx. I'm going to flip back just to practice. So the wrapper of our charms blow pop is bring the power down, decrease the power by 1. Now the candy shell is the sine function. So I'm going to do the cosine. I can't get to the gum yet till I get through the candy shell. Then I'm ready for the gum, which is the 3x. So I'm going to take that derivative as 3. So I might tidy that up as 12 sine cubed 3x times cosine 3x. All right, I'm going to pause, and I want you to try B, and if you're a fast worker, go on to C. Let's see if you can do this repeated use of the chain rule. So nice and slowly with it. All right, I'm going to start with B, then I'll pause again and let you work on C, but I want to make sure we're off on the right start. So before I begin this one, I personally would rewrite it. I need to for me. It's optional. If you need it, do it. If you don't, don't. So I would rewrite that square root as the quantity to the 1/2 power. All right, so here we go. So my wrapper is something to the 1/2 power. So I'm going to bring down the power, decrease the power by 1. So that was the wrapper. Now, the hard candy shell is secant. So the derivative of secant is secant x over 2 tangent x over 2. Now I'm ready to do the derivative of the inside, which would be 1/2. I don't do a half twice, okay? That's not what's happening. The inside of secant was x over 2. All right, so let me tidy this one up. And I want to show you what would likely be an answer on a multiple choice question. So I'm going to tidy, whoops, yeah, I can multiply, seriously. All right, so 2 times 2 is 4. Sorry about that. All right, I probably would not see this one as an answer. And let me show you what the answer might be as multiple choice. So like on a free response, you can leave it like this, first row. That's acceptable. This is acceptable on a free response. But where they're going to force you is on your multiple choice. So watch what they will likely do. They would have likely simplified like this and rationalized it. So then my answer might be secant x over, secant x over 2, but I could write that as the 3/2 power, right? You see where I got that from? This is secant to the first times secant to the 1/2. That would be 3/2 power. They probably would do that. Or they might have a square root of secant cubed x over 2. That's another option. So I just want you to see, anytime it's a type that I think they would have simplified it, I want to do those with you so you can keep seeing them. So like you can get yourself into a lot of trouble if you're never simplifying, because then you don't know how to do it, and they will simplify on the multiple choice. They will force it. So my suggestion is, on our homeworks, try and simplify when possible. If they're nasty, then don't. There's a few I wouldn't do if I don't have to, but I would just try to practice. All right, try letter C if you haven't already. This is y equals cotangent 2/3 power of 3x over 2. If it helps you to rewrite it, then rewrite it. If it doesn't, don't. Office hours begin today at 2:35. So if you have a question or concern about the Unit 2 test, come and let's talk about it. If you're really struggling with the chain rule today, come, let's get that ironed out. So we will enjoy office hours again. So happy. Okay, so I'm going to bring down the power. I'm going to decrease the power by 1. Then I'm going to scrunch it down here. What's the derivative of cotangent? Negative cosecant squared, right? Yeah. Yeah, I think you're thinking of cosecant. Then the derivative of the inside is 3/2. Oh, isn't that nice? The 2/3 and 3/2 cancel. So I get negative cosecant squared 3x over 2 all over the cube root of cotangent 3x over 2. I doubt they would rationalize a cube root. All right, natural logarithms and exponential functions. We're going to get through part of example 6 and then pause there because that's as far as I got with my other class period. The derivative of ln x was 1 over x. So the big idea for the chain rule version is it's 1 over the stuff times the derivative of the stuff. So sometimes you'll see it written as u prime over u. These properties are going to be helpful. We're actually not going to see that until the next class period together. But let's go ahead and look at letter A. If I want to find the derivative of y equals the natural log of 2x. So y prime would be 1 over the stuff, and then you have to take the derivative of that stuff. Well, what happens here? How does that simplify? Just 1 over x, right? Because the 2's cancel. So here's a note. If you have y equals the natural log of bx, the derivative is 1 over bx times b. It does not matter what the constant is, it will always cancel out. So that might, if you can begin to remember it, great. If you have to do the work and do it, great. It does not matter. But for some of us, I know we can hold that information in our brains and go with it. All right, letter B. The natural log of x squared plus 1. I'm going to take 1 over the stuff times the derivative of the stuff. That's it. You cannot cancel an x because x is not a common factor in my denominator. All right, now, this is in letter C. This is the first time that we're going to do a product rule problem. This one requires the product rule because I have x times the natural log of sine x. I have a variable x in both factors of that product. So I'm going to use the product rule. So I'm going to say y prime equals the first times the derivative of the second. So now I'm using the chain rule. The derivative of natural log of sine x is 1 over the stuff times the derivative of the stuff plus the second times the derivative of the first. Now, it just popped in my head. I hope there's no one that thinks that I have 3 factors here, okay? The natural log is of an input, okay? So natural log of sine x is 1 factor. It's not an ln and then a sine x. Okay, that doesn't make any sense. But just in case somebody was thinking that. So this is going to give me x cotangent x plus the natural log of sine x. Because cosine x over sine x is cotangent. All right, try letter D for me. Y equals the quantity natural log of x cubed. Does require the chain rule. All right, talk at your table. See if you got the same answers. All right, here we go. I'm going to bring down the power. decrease the power by 1, and then take the derivative of the inside, which the derivative of ln x is 1 over x. So then I would tidy that up to be 3 times the quantity natural log x squared all over x. All right, that's where I'm going to stop